Hi there and welcome to this video for Senior Physics on Electrostatics and Electricity. In this video we're going to explore charges in motion. Now charges in motion were first discovered by two physicists, Luigi Galvani and Alessandro Volta, round about in the 18th century. Now Luigi Galvani was basically interested in how nerves worked, and he basically came up with the idea that nerves required electricity and that we had a form of electricity flowing through him. So basically what he would do is charge up parts of frogs and limbs and pass an electric current through it or electric charge through it and notice that the limbs would move. And from this he deduced that basically electricity was present in all living things. Alessandro Volta is more famously known for the production of the electric battery. And basically what he did, as you can see from his very crude battery that he got here, he basically got some silver discs or metal discs, and then he soaked some paper in a salt solution. This produced ionization. The ionization of the salt solution then actually generated an electrical potential. That electrical potential then basically allowed charge to flow from one place to the next. So he basically produced the very first type of battery. And if you look around, there are batteries which actually still have his name of Volta. And from this we got the idea of voltage, voltage being this idea of electrical potential energy, which is present between two terminals, basically due to the electrical charge or those electrons. Now, let's just recap before we move on and look at how charge actually moves. Now, we already know that in order for charge to move, we need to have a conductor. And that conductor basically is made up of a free sea of electrons or outer electrons, which have the ability to move. And different conductors have a varying degree of movement due to these outer electrons, depending on how well they're held by the nucleus. We also know from Millikan's experiment that electrons are negatively charged, and we know that negative charge basically produces field lines which are acting in. They're radial field lines, and if we put lots and lots of lots and lots of electrons or negative charges together, they have the ability to repel. And we talked about that in the electrical fields post. Repulsion, as a result, causes force. The more or closer that we are able to push those electrons together, the more force we're going to generate coming backwards. And from this we get this potential difference that, depending on the distance that we place those electrical charges and the interaction of those field lines, the result is we are going to get a certain amount of energy once we release that force. And we know that electrons will move from an area where we've got large force to an area where there's little force. So we get this conservation of energy. So what happens in an electrical circuit? Well, if you look at this diagram here, all I've got is some atoms which are present in a conductor. Around them they've got this free sea of electrons, which is represented by those little black dots. Now we know that on one side of a wire we're going to have large numbers of electrons. They're going to be negatively charged, and as a result they're going to generate a huge amount of repulsion. So we get a large force. Likewise, on the opposite side, we're going to get a small number of electrons, relatively speaking, to the left-hand side. So we're going to get little repulsion. The result is we're going to have a small force. The conduit, or the wire, or the channel, is basically the ability for those electrons, or a place for those electrons to move from one place to the next. So the result is that we get this charge, these free electrons, to move from an area where we've got a large force to an area where we've got small force. Well, this is basically the negative side of the battery going round to the positive side of the battery. Now, if we just link up a battery with a wire, we're going to short circuit. Basically, we're going to get massive flow of electrons going from the negative terminal to the positive terminal. So what we do is we put a wee resistor in there, and what the resistor does, well, it actually slows down the speed at which the current can flow, or the electrical charge can flow. Now, as I've already stated just a second ago, basically this flow of negative charge in a circuit is called current. Now, this can also happen in a liquid. Now, those of you studying chemistry will have studied the idea of electrolysis. Now, how this works, on the right-hand side of the diagram you can see there, we've got an electrode sitting in a solution, which is an ionic solution. We've got a battery linked up to that right-hand side electrode, and what it does is it piles electrons onto that electrode. The result is that due to the ionization, we get this repulsion which is going to occur, where we're going to get the negative charge moving across to the positive charge. As a result, that's going to push electrons back into the battery. So as a result, we still get a continuous flow from one side to the next. So the net movement is going, in this case, from right to left. Now, if there is enough potential from one electrode to another, they will be able to pass through something which is not very conductive, for example, the air. And as a result, we saw that with the Van de Graaff, and you see it every day when we have a storm and we have lightning which is being conducted. Huge amounts of charge up in the clouds, very little in the earth. The result is that charge will jump, and that energy can be seen in the form of light. So we get this movement of charge which can occur. Now, in an electrical circuit, we call this flow current. So current is basically given the symbol I, and is used, the units of I, or current, is amps or amperes, after Pascal Ampere, who did a lot of work in looking at electrical circuits. Now, 1 amp is related to 1 coulomb per second. Now remember, we're talking about electrons here. So each electron has 1.6 times 10 to the negative 19 coulombs of charge. So within a 1 coulomb situation, we get 6.3 times 10 to the, I think it's 23 off the top of my head, electrons that make up 1 coulomb. Now really what an amp does is it looks at the flow rate. How quickly does that charge move through the circuit? Obviously, the faster it moves, the more energy flow I'm going to get, and we'll look at that in a little bit more detail. So, as I stated, 1 ampere or 1 amp of electric current is a flow of 1 coulomb per second, and here's the idea that we get 6.3 times 10 to the 18 electrons travelling past that point per second if we've got 1 amp of current. Now, in most circuits, we get a very, very small current which is likely to flow, basically in microamps or milliamps. In the laboratory, you may have some large situations where we've got amps, and you may think that's dangerous. But the reason why they're not dangerous is because our voltage is very, very low. We're always dealing with a very small amount of either voltage or current. It's the combined effect which is important. And it's the combined effect which we call power, which we'll study later on, which actually causes damage if you get an electric shock. Now, an algorithm was set up or was deduced where we were able to link together current, charge, and time. And basically what was deduced was that current, I, equals the charge, Q, divided by the time. And if you think about it, that's a rate equation. That is basically the amount of charge in coulombs passing a specific point per second, which is the unit of time. So I is the current measured in amps, Q is the charge measured in coulombs, and T is the time measured in seconds. Now we can measure the current in a circuit using an ammeter. And as you previously learned, that an ammeter basically has to be placed in series because it's measuring the flow as it goes through the circuit. So if you imagine the circuit as a loop, we've got a continuous flow. It's like having a dial or a anemometer, which is a wind speed generator, where you place it in the wind and it spins round. Imagine that in water, you would see that spinning around. Obviously, the faster the water flowed, the better or the faster the turbine would go. Well, really, the ammeter does exactly the same thing. It looks at the amount of charge which is flowing past a specific point. And as a result, it's always placed in series. Now, I've posted up some practical videos for you to have a look at with respect to current and how we would measure current within a a series circuit. So please watch those because they'll be a good way of getting you to understand exactly what happens in the lab. Now, there are two types of current that we can look at, and unfortunately, this is quite confusing. We have conventional current. Now, conventional current works on the principle that electrons travel from positive to negative. Now, this goes against everything that we already know. Why? Because we say that negative charge is due to, or the flow of current is due to repulsion from negative charge. So it should flow from negative to positive. But the trouble was when current was first, current and charge and electricity was first basically researched, they thought that the charge was positive. So everything was written going from a positive to a negative sense. It wasn't until later with Robert Millikan that they actually found out that it was negative, but by that point it was too late. So they've set up two conventions. We've got conventional current flowing from positive to negative, which is the old way of thinking. And we've got natural current, which is where we apply what we already know today, that it's traveling from negative to positive. Most of the information that we look at works on conventional current. So you sort of have to unlearn what you've already learned, which makes it a little bit confusing. But that's the way things go, and we just have to deal with convention. Okay, so let's have a little example of using I equals Q over T. So I've got here, and a very simple example, I've got 3.5 coulombs of charge past a specific point in 3 minutes. What is the current in the circuit in millicoulombs? So what I'd like you to do is pause the video, have a quick go at the equation. There's a little slip up, there's a little thing that you're going to have to work on, so watch out for any conversions, and then press play and we'll run through the solution. So pause it now. Okay, welcome back. So let's have a look and see how you got on. Well, it's very, very straightforward. Write down what you already know. We know Q is 3.5 coulombs. We know T is in 3 minutes, and we're going to find I, which is an unknown number of amps. We've got our algorithm here, which is I equals Q over T. Now, the first thing I have to work out is the fact that we're dealing with minutes, and T is measured in seconds. So I've got 3 minutes, 3 times 60 gives me 180 seconds. I know that I equals Q over T. Q equals 3.5 coulombs. I divide it by 180 and that gives me 0.019 coulombs. However, it does say in the question I want it in millicoulombs. Okay? It should be in milliamps, not millicoulombs. So the result is the answer should be I equals 19 milliamps. Apologies for the wrong unit there. So it should be milliamps, 19M capital A. So let's just recap on what we were talking about with respect to the circuit. Now what I've got here is two diagrams, and the diagrams basically will show exactly what's happening in this circuit. Now, remember we're going to be using conventional current. So we've got a water system here, and we've got the circuit which is represented by this water system on the other side in the blue square. So what you've got is a water pump which is going to be your battery. That's going to be producing the push. Remember, the push is as a result of negative charge repelling. So it flows through a pipe. Okay, now the pipe in this case is a conduit, which basically is a pathway which allows the current to flow. This happens to be the wire in the blue square. So it's flowing through the blue square. Now when it gets to the resistor, such as a light bulb, it's going to do work. Some of that energy is going to be transformed into another form of energy. Well, that's what the light bulb does. In the red diagram, it happens to be a turbine. All we need to know is that basically it's going to do some conversion from electrical energy, and it's going to use up some of that energy, and it's going to be converted into something else. On the left-hand side in the red square, we've got a flow rate meter. Now, this is the same as the ammeter, and it's measuring the flow of current. Now, the flow of current will be directly related to the push and also how much energy is required to flow through the turbine. The turbine takes up a lot of energy, or requires a lot of energy. Then the flow will be slow, and the flow is the net flow around the whole circuit. So basically, it doesn't matter where I place my flow rate meter or my ammeter in that series circuit, the flow will be identical all over the place. Okay, so you can sort of think of it like a flow of water. It's easier to understand, but note that we're actually moving in conventional current form from positive to negative. Now we have two main types of current that we use today. We've got DC current, and we've got AC current. DC basically is direct current, where AC is alternating current. Now they have two following wave patterns. This is basically a DC graph. Now you can see here that the current over time is continuous. Now this is what a lot of electrical devices like. They like a nice steady flow of current. They don't like going up and down. They don't like fluctuating at all. So in most circuits, we are going to have a nice steady flow of current. However, with AC, alternating current, it oscillates 50 times a second. This is how the actual energy is created in our power stations. So obviously, we are going to have to convert AC current into DC current if we're going to be using it in our devices. Coming out of the wall will be in the form of AC, so in the device there's going to have to be a way of converting it into DC. Now we will look at that in our electromagnetism unit. So check my electromagnetism unit out on iTunes U and download it, and you will see all the processes which occur for that. Okay, well, I hope this has made sense with respect to the use of current. The next video we'll look at EMF and voltage. If you go to the resistor or the resistance post, there will be a worksheet which will involve some of the I equals Q over T equation practices. It's all on one sheet. So download that worksheet. There's an answer sheet there for you to use. And yes, I hope you found that useful. Okay, well, thank you for joining me. I look forward to you joining me again. Bye for now.